All right, we have this chart here, and hopefully this chart's familiar already to you, but just a refresher, 10 to the fourth, it really means 10 times 10 times 10 times 10. And if you look at all these zeros here, there's 4 of them in the factors, and so there's going to be 4 over here when we write the number in standard form. That's the convenience of using 10 as your base number. And whatever the exponent is going to tell you how many zeros you have once you write it in standard form. What I want to do, I just want to show you something, a cool pattern that you might have already picked up on and maybe haven't. But if I take 10 to the first and multiply that by 10 to the second, what I end up with is, well, 10 to the first is just one single 10. We see that right here. And 10 to the second is 2 more 10s. And there's a time sign right there. So that's 10 times 10 times 10. Notice there are 3 10s here now. So 10 to the first times 10 to the second is the same thing as 10 to the third power. And if I was to actually multiply this out, it would be 1,000. And we got that same number right over here. So it looks like, based on this, if you just take the exponents and add them together, you end up with the new exponent. So if you're multiplying by the same base and add the exponents, it seems to work. But let's verify. This might be a strange coincidence. You know how you might say, as an elementary school student, oh, 2 times 2 equals 4. That's just like 2 plus 2 equals 4. So multiplying and adding must be the same thing. And we'd say, whoa, 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 slow it down there, right? So we're not going to go too crazy yet. Let's just try to experiment some more here. So if I did like 10 to the second times 10 to the third, let's try that one. And we want to try to prove, like we said up here, we add these two exponents, it gets us the new exponent. So we want to prove, is this equal to 10 to the fifth or not? So I'm going to write it out. 10 squared is 10 times 10, which we eventually will know is 100. And just so that we're clear about what 10 to the third is, because you can lose track, I'm going to underline this in blue so that you know the 3 10s I write down represent 10 to the third. And it looks like in the end here, how many 10s am I multiplying? I forgot to put this time sign down here. But I'm multiplying 5 10s in the end. So yeah, it looks like this is the case, that 10 to the second times 10 to the third is the same thing as 10 to the fifth. And we kind of just proved it right here. So if I can, I'm going to do a few examples for you right now, and just to show you kind of the general gist of this. So the rule is, if the bases are the same, when you're multiplying, you can add the bases. So some more examples. Problem A right here. If I have 5 to the third times 5 to the fourth, that should just equal 5 to the seventh power, right? I would write out, let me do it out actually, just so you see it. 5 to the third is 5 times 5 times 5. 5 to the fourth is 5 times 5 times 5 times one more 5. So you can see I highlighted in purple. 5 to the third, that's 3 5s. 5 to the fourth, that's 4 5s. And since I'm multiplying these two together, in total I'm multiplying 7 5s, so you can say that it's 5 to the seventh power. Problem B, I'm just going to throw a little wrinkle at you. 3 to the fourth times 3. Now you might notice there's no exponent up here. Uh-oh, it's naked, so what we can do is put some clothes on it. And all that we can do is just put that 1 right there. 3 to the first, as we know from the chart, anything to the first power is just itself. So 3 to the first is the same thing as writing 3. So that's why I'm able to do that. So now I can add these together, and that'll equal 3 to the fifth. Problem C, if we did 3 to the second times 3 to the negative fifth, this will equal 3 to the negative third. You just add those exponents together. 2 plus negative 5 is negative 3. Problem D, again, I'm going to try to confuse you a little bit here. If I have G, that's a G, not a 9, to the M times G to the N. And this is abstract. This is a little bit difficult. But just go back to the rule. If the bases are the same, which they're both G, when multiplying, add the exponents. Your exponents here are M and N. So this is the same thing as G to the M plus N. I don't know what M and N are. It doesn't say. So I just say, for my answer, G to the M plus N. 5 squared times 4. It looks like these have different bases. It says if the bases are the same, when you're multiplying, you can add the exponent. So I could put a 1 on here, but it doesn't make sense to do that, because if I were to multiply this and call it 20 to the to the third, let's just say hypothetically, like I multiply the bases, which I shouldn't do. 20 to the third is 20 times 20 times 20. I know 20 times 20 is 400, and 400 times 20 is like 8,000. In reality, all this number is, if we do order of operations, 5 squared is 25, and times 4 to the first is just 4, is 100. So this makes it way too big. So you just want to, if you don't have the same bases, the rule, you can't really apply it. So before you add, if that problem has exponent expressions with the same base, then combine the exponents to save space. It sounds kind of boring if you say it, so let's sing it. So before you add, if that problem has exponent expressions with the same base, then combine the exponents to save space. Again, so before you add, if that problem has exponent expressions with the same base, then combine the exponents to save space. Oh yeah. So given that rule with multiplication, if the bases are the same, when you divide, subtract the exponents. Here's some examples of what I mean. Let's say we had 6 to the 5th divided by 6 to the 2nd. 6 to the 5th is the same as 6 times 6 times 6 times 6. And you divide it by 6 times 6. What you'll notice is your denominator and your numerator are the same number. This kind of goes back to something you learned with fractions. I'm just going to write a little scribble note off to the side here. But if I have 10 over 10, that's the same thing as 1. 10 divided by 10 is 1. Or if I have 2 halves, that's the same as 1 whole, right? So 6 over 6 is really equal to 1. So these cancel, and so do these. And you're just left with 6 times 6 times 6, or 6 to the third power. Let's look at another example. Example B. I'm going to get a little trickier here. If we have 10 to the 7th divided by 10 to the negative second, not the positive second, what you're going to notice is I subtracted up here. So we have to subtract 7 minus negative 2. And this goes back to adding and subtracting integers. You have to add the opposite. So 7 plus positive 2. So believe it or not, you're going to have 10 to the 9th power. That's a very big number. Hopefully you grow up and have that much money. 10 to the 9th power. Problem C. I've got 5 to the 4th over 5. So again, if that 5 is naked, you can just put some clothes on it and make that a 1. And now we just subtract those, and it equals 5 to the 3rd. So we're dividing. Problem D. If I just use variables, let's get it abstract again. We have p to the n over p to the m. Well, the bases are both p, so I am allowed to apply this rule. The bases are the same, so we just have to subtract the exponents. The exponents are n and m, so we would do p to the n minus m. And finally, example E. I'm going to go a little bit of a challenge here. 6 squared over 2 squared. So our rule says if the bases are the same. The bases aren't the same here, but the exponents are. And I'm going to show you this first of all done out. I know 6 squared means 6 times 6. So 6 times 6 is 36. 2 times 2 means this is going to equal 4. And if you do 36 divided by 4, if you do that out, that's going to equal 9, right? 4 times 9 is 36. So that equals 9. If I was to start with this problem where it was originally 6 squared over 2 squared, what I could say is right from the beginning, okay, the exponents are the same. How can I end up with 9? Well, if I just do the base divided by the base, that equals 3. That's not the answer. The answer is 9. So leave your exponent on, and I think that would be a way to get you 9. I'll leave it to you, the math student, to experiment and see if that actually works all the time. If the exponent's the same, that you can actually save some space that way too. Speaking of saving space, let's sing a song. So before you add, if that problem has exponent expressions with the same base, then combine the exponents to save space. That's this one right here. The base is the same. This one right here, the bases aren't the same. It won't work. So if you divide, If that problem has exponent expressions with the same base, then subtract the exponents to save space. Notice this one right here. They don't have the same base. Won't work. They don't even have the same exponent this time. That's all I got. Hope you like it.